first of all, the basic simple question. So since you're working with vision, rather computer vision, so what is the basic simple mathematics of an image? Mathematics of an image is represented as a matrix. Okay, a 2D matrix, let's say a grayscale image where each pixel is a number between 0 to 20, like 0 to 255. Now the question is that how do you represent a colored image? You have multiple channels out there. Okay, so this is how we represent a colored image. But let's assume that our image is a tensor, which is in general like a 1D tensor is a vector, a 2D tensor is a matrix that you can see here in the screen. It's a matrix. And when you have color channels, they're 3D tensors, so that becomes a 3D like something like this. So in general, that's why we call it tensor. And if you code it out in PyTorch, it's also called a tensor. So I would say it's a tensor. But since we are low dimensional creatures, you can even think of an image as a matrix mathematically. Okay, so next question is that what are the different computer vision problems? So the this slide is actually taken from Stanford's CS, I forgot the name, but Stanford's computer vision course. You can go and check it out after this. So the basic computer vision problems are: number one, you are given an image and you are asked what, like there are single objects and you're asked what type of animals or what type of object it is. So it's called classification. There's also, you want to localize and then classify. So that's classification plus localization. It's single object, but there can be multiple object too. And that's where segmentation and object detection comes. So object detections is detecting what objects are there and also telling which are them. But semantic segmentation is going a bit deeper. It's segmenting those regions properly. Okay.
Motivation.
Sorry. Oh.
Yeah, that was one. You can ignore that.
Yeah. So yeah, so object detection, and further deeper layer is semantic segmentation. There are also other cases when you combine object detection and segmentation, where there are two cats. So you want to name one cat, cat 1 and cat 2. So that will be different colors. So that's called instance segmentation. But these are deeper layers. But the core idea, I will say, is the core three problems are classification, object detection, and segmentation. Now, the next question that comes up is that, is there any structure? And yes, there's a unifying structure to solve this computer vision problems. So what is the basic structure? Let's say you have an image of a door, and so you first encode this door into a tensor. You first, this is an encoder. So you can think of encoder as a function, okay, which has some parameters theta. So you have an encoder, you get a tensor, and out of those tensors, you build different kind of architectures for the decoder part. So if it's a classification problem, so what you want to do is that if it's a classification problem, you don't want the entire information, you probably want smaller features. So you reduce the number of features to get to the single score. So that's a different kind of decoder, you can say. So these are all different decoders. So here you reduce the number of features to get to this simple object. Okay. When you want to do when you want to do segmentation or object detection, what you need that full scale of the image, right? Full scale of the image you need. So often there's a U kind of structure, like when you encode to a low number of features and then you decode to get the full spatial resolution of the image. So deep lab, UNet, all these things work on this kind of structure. And same for object detection. If you read about all the object detection techniques, often all these three things are done together in something called masks or CNN. So, but the main part is this. The main part is this part. So you see that all of them. So often what people do is that using that same, yeah, as I said in mask RCNN, we use the same encoding, the tensor, to do all the tasks. So you see this, all of them has this labels out there, this object detection, this segmentation, this code labels out there. So you're using this encoder to encode the specific tensors, and out of them you're building this other parts for separate task. Okay. So now I repeated this a few times. The reason is that this will come back. We will come back to this again. The whole goal of self-supervised learning is to just, without the labels, we delete this part. How can we learn just this part? That's the main question of self-supervised learning. Okay. The reason I did this is that all of them has the same encoding structure. Okay. And this tensor is something called, so it's not related to vision, but this kind of tensor, Geoffrey Hinton has actually, I hope all of you know about Hinton. Uh, he called something as a thought vector, but that's for language. Okay. That's for language. So I am extending it, the nomenclature, to something called a thought tensor, because it can be 3D too. Now, why I am calling it this specific word thought? This is inspired by the very brain structure. So the main question is that how did the brain structure, from where the term neural networks came in, inspired this hierarchical structures of this feature detection, feature extraction? Because it exactly happens in the brain too. For example, I will not go into details, but let me tell you the basic idea. For example, you have the eye here. It goes through the brain to this final visual cortex. So here's the eye, it goes through the brain to the final visual cortex. And from there, two different branches flow out. This branch is called the dorsal branch, dorsal stream. And this branch is called the ventral stream. So the dorsal stream, these are all like recorded, these are all done. These experimentations are done by the neuroscientists. And this dorsal stream actually has something called the spatial context. And this ventral stream consists of the content, the object context or content. For example, to give you an idea, for example, when you have this door, I should probably just give me a minute. So for example, when you're doing this classification, okay, probably you just need the features of, okay, there is brown, there is a woody kind of texture, or there is a door handle, this kind of, you don't need the entire spatial resolution to detect if it's a door or not. So that's why there's you reduce the spatial structure. So classification for that, whether the door is open or not, the classification needs the object context, not the entire spatial context, right? And so often what I feel is that this object, this ventral stream, is similar to the classification branch. And the spatial context gives you the entire spatial mapping, just like it happens when you want to segment this region of the door. You want the entire spatial resolution, right? You want the entire spatial resolution for doing the segmentation of the door. So the spatial context gives you this object detection or segmentation kind of idea. And when they are combined together, you can observe that this kind of structure comes up. Now you can say, why are there so many layers? The reason again lies in the brain structure, that you have a hierarchical feature extraction. The image goes to the brain and it goes step by step. You can see here probably there are structures called V1, V2, V3. So for example, the V1 actually captures the edges. The V2 captures more detailed structure. So that's why this whole hierarchical structure of neural networks came up. Yesterday I was doing experimentation of just simple experimentation. I saw that the convolutional network first captures lines and then they combine by compositions, because this hierarchical structure is nothing but compositions, right? Like you can compose three lines to make a triangle, or if you make the number of lines bigger, you will get a circle, right? Let's say if you have a line detection like this, so you make a circle. So this composition, so this hierarchical structure is nothing but composition. What this says that our brain has evolved over time to look at objects at in a hierarchical sense. First simple objects, then compose to make a complex object, and this carries on. And that's why deep learning is so useful. And interest this neuroscientist who, it's actually from 2024 or 2025, early this year, they developed this and they saw this, they wanted to build this similar structure of how, as I said, the spatial context and object context, and they realized that this actually works well, and this is very similar to the mask RCNN framework. If you go and read up, I'm not overwhelming you with the words. What I'm trying to say is that you can go back and read about this and have a better understanding. So this brain structure, to remind you, number one, it has a hierarchical structure, and this hierarchical structure captures hierarchical features, and this is inspired by the brain. Now the question is that what are those hierarchical structures made of? What are the encoders? What are each individual feature extractors? How do they look like? As of now, there are two fundamental feature extractors. One is the convolution, one is the vision transformer. Okay, so I will go to them one by one. So why convolution? So I will assume you know convolution. If not, I will slowly describe it. Convolutions are nothing. If you have an image, let's say you have an eye and a smiley, and you want to detect the smile, so you have a filter of the smile. Let's say you have a filter like this. And if you convolve, like if you run it over each of the part of the image one by one, you will get something like this. Everything is will be zero because there is no such smile everywhere, but only at the smile region you will get something like 111. That means okay, it's present. So this is kind of detection, like detection in the sense that okay, if this filter has it, if this filter has information about that specific object, and each of these filters, for example, you can build another one for eye, another one for left eye, another one for right eye, different. And again, the circles can be again be built up using lines. So the question is, most important question is that previously, before the deep learning, what happened was all these people used to handcraft these features. But now, in the era of deep learning, what they realize with large amount of data, these features automatically comes up, are learned. So each convolution is, or each convolution filter is a feature extractor. And we are learning this from the data. And this builds this entire architecture of the CNN. And these are the hierarchical structures. This is level 1, this is level 2. And at each level, different information are being learned. Now, in this process, two things came up. In this process, one important aspect came up was this ResNet layer. So this residual connection does what? So as you learn this deep hierarchical structure, often the earlier information gets lost, which may be important for the later layer detection. So they added this skip connection, and this built this general architecture, this general layer, which they call the residual block. Okay. Any questions till this point of time, guys? Any questions? Okay.
I have one question.
Yes, please.
So initially you showed an image where there is a box, then there is a cat and all, which are like separate objects.
Yes.
But here what you are trying to say is that uh, it's a composition of different features. Let's say a right eye, left eye, which is of one image. And it might be the next feature would be small hair or the eyelash or something, which is like the composite. Like when I try to identify the cat, it should have these kind of features, so the features are the nested inside. So
Yes.
that's what you're trying to say, right?
Yes. So what I said is an example. Okay. This is actually, yeah, I mean, this is an example. Yes, you're right. But not all features are interpretable. That's why the whole interpretable AI is there, because all these features are not interpretable. So coming to your question, if you visualize these features out there, you will see that this is the initial layer features, and you can see it kind of detects edges or colors. Okay. Now the same filter is evolved over the image, so is moved over the image, so it detects, okay, there is this pink color. So for example, this yellow detector will probably look at this region, this yellow region. Okay. The green detector will look at the grass and say, okay, there is green aspects out there. So not always it's interpretable. But again, as you can see that, for example, this eye feature came up here on the higher level features. Okay, so you can see that it goes from the simple features to the mid-level features to the high-level features. Okay, did you understand?
Yeah, so it is like narrowing it down and drilling it down to the smallest feature.
You can say that, or you can say that there are multiple levels of features out there. So it looks at all the features out there. So let's say there is an image. When there's an image, initially, if you squint your eyes, make it small, you will see overall small level features. But if you want to go deep into it, you need more features. But both the features are important. No features is less important. Does it make sense? So
Yeah,
all the
understood.
features are important.
Understood.
Yeah,
It's like a tree levels look where
exactly.
overall.
Exactly. That's the hierarchical structure. So it's a tree level
Understood.
structure. Exactly. Yes. Very good. Yes, Dionkar. Okay. Yeah. Are there any other person who has
Yeah,
questions?
so if I have to visualize this, so basically it's a kind of first hazy. We will have a lot very basic shapes or basic edges, and then when we are zooming it, we will be getting details, next level details like that, right? So
Absolutely.
for at the first level, it will be like very basic shapes, maybe lines, such type of things, and then the next level it becomes those lines will be joined and then created a next shape.
Yes.
So such every stage it will be like more detailed shape coming. Is it
Yes. Absolutely. Fully agree. Yes.
okay? So you mentioned the first previously people used to make
Yeah.
these things manually.
Yes.
So that means that when they're doing manually, they were doing like this only, or they were just taking one particular shape and then trying to do it, or how it is that
So a very,
difference
very good
manual
question.
to
So they actually looked at different images visually and they saw, okay, this may be useful, and this kind of feature extractors they have built. Yes. So for example, you're detecting a brain tumor. So they build like a feature that is close to a brain tumor and then took that feature and then convolved it and saw that which has that one. Make sense?
yeah. So
Yeah.
in JPEG 2000, or I think I'm not very sure in the image processing, there is a different type of things similar to this. So it will be hierarchical encoding happens. So it's a very similar concept, or it's a different concept.
I really do not know about the JPEG
Okay.
one you said, so I have to learn about it.
Okay. Sure. Okay. Thank you.
Yeah. But I mean, I'm glad you observed the connection. I'm sure if it is an advanced one, it should be. But yeah. But absolutely. Thank you for that. So yeah, so this is the basic idea. It keeps on increasing this level of features. And this is exactly what the Ankur said, that when you zoom in, we have more detailed features. And that's what this is doing. And when you zoom in, actually the higher parts of the brain, the deeper parts of the brain are getting activated. So it's inspired by the brain. But recently, this encoder-decoder structure of the VIT came up. So all of you are familiar with transformers, the basic idea of transformers, guys? Or do you want me to explain that a bit? Okay, so let me explain a bit. So for example, okay. Okay, so I will take, for example, okay, so let's take this image. So the image, instead of language, in language we have words, right? Word 1, word 2, word. Let's say 10 words are there. So each word is changed into an embedding, right? In a vector, is given a vector that is learned. So now what in image, what happens is that instead of words, they broke the entire image into patches. Let's say 16 cross 16 or 8 cross 8. For example, like this is patch 1, patch 2, and these patches are given an embedding. So the CLS token, as you know, in language also, the CLS token stands for classification. In other words, the CLS token is very similar to this last layer here. This last layer here after this. So it's a global kind of feature extractor of all the patches together. So the CLS token has an attention to all the patches, right? So it has information about the global information, about global in the sense all information. It can, you can see, like it's like overall information out there. This is important because this will come again in multiple aspects of DINO. People use this information. This is a very important aspect. Okay, so each of these images is then transformed into an embedding. Okay, like this. And let's not look at the layer. I'm not going into the details of that, but here the multi attention happens exactly like the attention happens in language. The only difference is the pre-processing part. In text, each word or token is changed into an embedding, but in image, each patch is changed into an embedding. Okay, so yeah, this is important. And the positional encoder part has multiple new innovations. So initially it was like 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the position encoder. Understand, it's all the tokens are attending to all the tokens, but they are now also 2D encodings. There are multiple different encodings, which we can talk about later. But yeah, the positional encoding, you see that the vision has a more importance of spatial positional part. So can that be manipulated, or can the information be used? Those research are also happening. So these are, very recent stuff. But what I want you to focus on is the similarity. So you see that there is a hierarchical feature here, right? And each of them is a convolution. Rather, each of them is a convolution block. You can sometimes, like, each block looks like this. Okay, this has convolution in it, and all this batch norm, really all these things are for optimization purposes, for stabilization purposes. Okay, but the main idea, main coding, main fundamental stuff is this convolution filter. But in vision transformer, the main fundamental part is this transformer, the self-attention or multi-attention part, each individual feature. Okay, that is also interestingly a matrix. So the self-attention part. But this is the basic idea. So one is the convolution, one is the attention. Okay, did you understand, guys? All of you, did you understand? I hope I do not need to go into much details more than this. All good? Okay, please feel free to ask questions. Okay, now this slide will take some time, and I want to actually spend some time in this slide. Is what are this transformer layer learning? What are the fundamental aspects of this transformer layer? And this image is, you cannot understand what it's doing, so that's why I need to explain. So the question is, this is from the paper 2021. Actually, it's a native paper which says that do vision transformers see like convolutional neural networks? For example, in convolutional embedding technique name. So one is this embedding technique is just normal linear projection, and in this positional encoding, it's also similar to the positional encoding scheme, the sinusoidal and cosine curve that you have. But recent developments include something like alibi or rope rotatory positional encoder. So these are very important aspects. So I will not go into that. That's a totally different direction altogether, but very exciting stuff. So I will not go into that, but you can. This is an important positional encoding new stuff. For pixels, each. So it's not pixel wise; it's patch wise. Each is converted into just a linear projection. That's it. Just a linear projection. But in other many other, so there are different approaches. Okay, many people apply convolution because they want to restrict that, have that inductive bias of the convolution. But many people just project it, like unroll it to a single vector and then do a linear projection to get this. Does it make sense? Yeah. So there is no name for it. This is like, yeah, there is no name for it. Yeah, absolutely. Okay. So the question is that what are the transformers? Absolutely, my pleasure. So what about transformers layer learning? So if you see this convolutional neural network, they have a structure which it's not very obvious, but due to the small filter layers, it's receptive field, the region it's looking at, it's small, and then it becomes bigger, and then it becomes bigger, and then it becomes bigger. So this conv-net has a very local, and then it increases to global, slowly, layer by layer. Okay, but in vision transformers, rather in transformers, it's the attention. All the patches, patch 1, patch 2, 9, each of the 9 patches are attending to each of the 9 patches from the very first layer. From the very first layer, they attend to each other. So there is instantly a global connection right away at the beginning. So that's why natural question comes that if convolution, it slowly increases the receptive field and makes it from local to global, then does the vision transformer look like that? And it turns out that no, it doesn't look like that. It looks in a very different fashion. So this residual network is, let's say, the CNN part. And you can see that so what it is doing, so there are multiple layers, and what they're doing, they're capturing something called a CKA, but let's not go into that. They're capturing how 2 layers are very similar to each other. Okay. So all the 120 layers, sub layers, and you can see that they are clustered in 2 different regions. This tells you that this is kind of local capturing, and then slowly it moves on to capture in a very global manner, because the receptive field increases after this special point. But in VIT, you can see right away from the beginning, all the layers are similar. They're looking at a very global structure right away. They are very similar. And we cannot say that whether it's a global or local from here, but they are working in a similar fashion. And what they did was this query, this simple experiment. So what they did was, among these patches, these maps. So this is from the paper, do vision transformers see like CNNs? So there's a okay. So yeah, what I'm saying is that each layer, there are two matrices. So two matrices, we are finding the similarity between two matrices, two attention layers. So each point is saying that how much two layers are similar in their feature extraction. Does it make sense?
If they are,
Devendra?
if they are more lighter means they are more similar, and if they are darker means they are apart. Something like that, is it?
Yes. Yeah, you're right. Gram matrix. Yes, you're right. Very similar to gram matrix, but not exactly. It's the mathematics is very similar actually to gram matrix. Yeah, but it's called CKA. I forgot the full form. Yeah. So you can check this paper. Do vision transformers see like the mathematics is given over there? Yeah, I'm not going into too much of details because this is not the core idea of the class, but I want to help you develop your intuition for the rest of the time. Okay, so what they observed is this following. So they observed the distance between which key and query has the highest match, and they observed the distance between those key and query. Naturally, every word has the same, or every patch will have the maximum overlap, the attention's weight to its own, to itself. So then it looks at the next highest one, and next highest key which has the maximum overlap, cosine similarity, or dot product with the query. And they saw that how these are far apart from each other, how these two pixels or two patches are far apart from each other. These two patches are far apart from each other. They calculate that, and they plotted that mean distance with the different uh, attention heads. Like attention head means in relation to the length, what should I say, the number of layers. And what they observed is that for the highest block, which block is much deeper, it is only looking at global, like the distance is large. That means the pixel distance is large. That means it's looking at a very global way. There's a global transition, global attention all over the patches. But for lower layers, it initially increases. So understand the sorted self-attention because there are multiple attention heads. So what they're looking at, that as at the initial attention heads, it's local, but as you increase the attention head, it becomes global. So it's local to global, and then it's local to global, and local to global, and after a certain time, it's just global. So it's initially local to global, local to global, local to global. It increases with number of attention heads, and then finally, it's global here. So this transition happens. Does it make sense, guys? All of you? Any questions? Okay. So the next part is yes. Okay.
I think Divakar has his hand raised. Divakar, you have a question or?
I think it's mistakenly raised. Okay. So the next part is this skip connection. I want to just say this because you may wonder that there's a skip connection here. Why am I taking the skip connection? Because the skip connection is very important both in CNN and vision transformer. Oh, okay. That's a whole. Okay, that's a very good question. So, Devendra, that's a very good question because we need so many layers because brain looks at a hierarchical fashion. We need more layers to get more hierarchical features. It looks globally, but the feature details need to increase, and it needs to become more. We need to have more compositions, more depth, because that's how brain looks at. What I'm saying is that the convolution structure. Initially it's local and it goes to global, but a more important idea is the textures that it is learning, the convolution of the detailed feature it's learning, composition of features from low level features to high level features. But in VIT also it's the same, but we are replacing that. So there are two components. One is the local global, one is the quality of features. The quality of features increases with depth. It cannot just happen with just that. I mean, it cannot just happen if you have just one layer of entire global. So there is a local to global crunching of features that is different in CNN and VIT, but there's a hierarchical fashion of feature extraction too. Two complementary components. So that should remain same. That's why depth is important. Does it make sense, Devendra?
I have an analogy. Can
Yes,
you
please.
correct me if you're wrong? So
Yeah,
this
sure.
CNN would be something like, let's say there is a person image with a person. It will just, the overall will identify whether it's a person or not. In depth, in the second level, it will identify whether it's a man or woman. On the third level, it might identify, okay, it has got a blonde hair or not. Like more features. Whereas this VIT will identify, will take one part at a time, and it will try to identify whether it has got that feature or not. Like
Yes.
one patch at a time, something like that.
Yes. Yeah, but I will look into. You're right. I will look into what Devendra is saying towards the end. But yeah, great question, I believe. Okay, so Divankar has question, but that can wait. Okay. Yeah, please keep on asking questions. Another important feature what they observe is that the skip connection is very important to retain the features because the features decay over time. The skip connections keep on reminding that okay, from the previous layers, and if it is not, if you remove the skip connections, you see two different feature extractions here. And this is also another reason why yeah, so this is also another reason why you need to have a skip connection, that it so that the it keeps on reminding the network that okay, you don't forget the what you have learned previously, the low level features. Yeah, so this is important. Any questions in this slide apart from Devendra's one? Which any other questions? Okay. So now what is self-supervised learning? So this is where we come from the entire discussion. So we have two feature extractor kind of blocks. One is residual, one is VIT, the vision transformer based. But coming back to this slide, that we want to have a uniform structure to solve those vision problems. So we have this encoder part the same. So the question is that if we do not have labels, then how to have such a thought vector or a good tensor? So rather, how do we define a good representation of an image? And that's what self-supervised learning is all about. Okay, understand we have no supervision. Another question that before I go on to how to evaluate, another question that comes up is how to, before I go on to discuss what is self-supervised learning, one important question that comes up is how to evaluate self-supervised learning. The way to evaluate self-supervised learning is the following. You have a self-supervised training framework which gives some good pretext, like the good representations. You want to take those representations and then fine tune on a classifier, whether for a classifier or whatever, segmentation, object detection, whatever you are doing. For example, in DINO that I will briefly discuss about, they saw that with just those representations and just adding a KNN layer, K nearest never, with the representations learned and adding a KNN layer, it really gives high accuracy, almost similar or better than the supervised learning of ImageNet on ImageNet images. And also another way to visually understand is that the clusters, they are the similar representations are clustered together. This is also one way. But yeah, so say the evaluation of self-supervised learning is totally another different discussion topic. today's main goal is to understand how the self-supervised learning has evolved over time. The first self-supervised learning that came up is the autoencoder from early 2000. The whole idea was as an image, you encode, and you try to recreate the image. And in the process, you find this latent space representations, these representations. The issue with that they found out that these are very trivial they're very trivial mappings. They are not looking at what it should look at the image. They are just mappings so that they can construct the pixels back. So the reason was it was pixel level, not object level, because not concept level. There is a concept. Let's say in this picture there is a face, there is hand. So the objects are not there, just the pixels are there because it's a pixel level reconstruction. We will see later on the simple idea has been transformed a bit to get a different, better autoencoder decoder structure. So, okay, all of you understood about this simple autoencoder structure, why it doesn't work? It mostly pixel level reconstruction. That's why they do not look at the concepts, but just the pixels. So that's why it's low level features, bad features. Then came the core concept of what is pretext task, which is also there in language. So what it does is that, okay, what I will do is that I will apply some simple augmentations on images or remove the image features and try to recreate the image features. Okay, so what was that? For example, in this case, they remove the color and they try to recreate the color. Of course, there's a learning. So the self-supervised can be represented as X, and there's an encoder, and there is some features, small e, and then the decoder, and some X dash, which is kind of a different reconstruction of the image. Okay, or maybe X dash to X. So in this case, X dash is nothing but removal of the color. In this case, just removal or cropping out one region. In this case, it is rotating the patches out there. Like it's called a jigsaw puzzle. Essentially, what we are doing is that we are transforming X into X dash by some augmentation and try to recreate or remove that augmentation to get the actual image. Another one was it rotated all these different features and then try to predict which rotation it is. Okay. Again, this is really position. It's trying to predict where these two patches are. But the whole idea was specific augmentations on images and try to recreate the actual image. And this didn't scale up properly. And the next part was what transformed the entire SSL. To understand why the next part is important, we will spend some time to understand and do this 2D thought experiment to build this entire 3D of SSL. So let's say you have these two circles, two data which we do not know, they are unlabeled, but we can clearly see a structure. Okay. So we want to have a single representation, a vector or a number that helps us build, which helps us recognize that these two are different. So what that number would be? Can anyone tell me? Let's say out of these 2D points, I want to extract only one number. Okay. What that number will be, which can ideally discriminate this single number. 1D. Anyone? Any idea? Very good, Devendra. So the radius, x square plus y square, right? So it's a single number. So the question is that we want, very good, Devendra. The question is we want to learn that r square. How to learn that? So we want to learn that r square. How to learn that? this is how you can think of it. And this approach is defined, actually is borrowed from a mathematical idea. So in the 19th century, geometry of an object is defined as the properties of a space, it's a 2D space or 3D space, or invariant means which is not changed, which is not varying to certain augmentations. I'm not telling the full sentence, but it's invariant to certain augmentations. For example, the 2D space is invariant to the distance, the distance don't change like that. Okay. For example, if you rotate the 2D space, the 2D space will remain 2D space. The distance doesn't change. In fact, not the distance, but the angle doesn't change. Similarly, here, can we think of a similar spatial version of it for images? Can we think in an image format? What can be that? And we will exactly try to recreate that in this specific case. So if you have an image X, what we will do is that we will look at two different augmentations of it. For example, in this case, how to get that R square? That's the main question, right? So if we have this, okay. If you have this two dots, what we can do is that we can apply an augmentation on it. What kind of augmentation? That's an important question. In this case, we will just rotate it. If you rotate it, it will kind of remain the same. Probably the positions will change, but the whole structure, if you rotate this property will remain the same. This spatial geometry of the two 2D clusters will remain the same, like this. And we keep on rotating it. So what we are discovering is we are trying to understand what doesn't change when you keep on rotating this. The question is that what doesn't change? And the answer is the radius. The radius doesn't change. And if you plot the radius, it will be something like this. And this one is the blue one, and the bigger one is the red one. So understand the structure, what they did. They took a spatial geometry, this 2D points, and they augmented it to create a view, a different view of that 2D points. And then they asked that what didn't change. So what they're trying to do, they take the same image, they looked at two different augmentations. It'll look the same. And then they try to see what doesn't change. Let's say this will be E2, this is E1, and this should be same. And what doesn't change is the radius. And that's why it's a good measure. Does it make sense, everyone? Any questions? Any questions out there? Okay. So similarly, we will approach, oh, thank you. We will do the same thing on images. We will look at two different augmentations, but understand, here if you have taken a different augmentation, okay, if you have taken a different augmentation, let's say of, like making like this, like changing an ellipse, like shearing it, changing a circle to an ellipse. This will this will not hold again. So choosing the augmentation is very important. This augmentation should be very specific to the geometry of the input. So in image, this augmentation should be very specific to the image. You shouldn't take any generic augmentation. And we will try to understand, so out of this we will try to extract two embeddings, and we will try to decrease the distance between them. Okay, so there are questions. Choosing the type of augmentation is important, like if you multiply. Yes, exactly. So if you, that's very important. So in image, what kind of, so you can see the pretext task, in the pretext time, they chose similar augmentations, some augmentations like coloration, this masking, and all these things, rotation. So those augmentations should be very image, like the specific to the domain, the data set of image. For text, it will be a different augmentation altogether. So that's where the geometry, the data information is coming out. So you have an image, you have two augmentations, and those augmentations encoded features should come together. That's where the invariants come in. Okay. So reminding you, so there are two augmentations, x1, x2, f, the same function. And the whole idea is that the z2 should come together. f1, x1, and this should be low. So this will solve the problem, right? Yes or no? So all of you understood this will solve the problem, right? Any questions? Unfortunately, this will not solve the problem. Yeah, exactly. Good, Devendra. Unfortunately, this will not solve the problem. This problem will not be solved because understand that what we are trying to minimize. We are trying to find the theta such that this is minimized. If the distance between if this two gets minimized, right? Now, can someone tell me that what is the best solution to this? This is minimized. What's the global minima? And when is the global minima achieved? Any idea? I know Devendra knows the answer. I know that. Very good. Okay. Yeah. Good. So it's minimized when all of them are constant. That f of xi is constant. Not just constant, there are different other aspects too, where it can be in a low dimensional subspace and other places. I am not going into details of it. That will just confuse. But the simple idea is that this loss is minimized. Loss is 0 if all of them are constant. Actually, we are minimizing the loss. Everything is constant. So we need a different mechanism to remove that constant. Like we need another, like the same idea in GAN, we need a discriminator and generator kind of so that it balances out each other. Okay. So that's where the contrastive learning came up. So in contrastive learning, I will not go into the details. They created an idea of negative pairs. Yes. So did you understand that the minimization solution of this is actually, this leads to loss is equal to 0 only when all of them are the same diameter. All the embeddings are all the E1s are same. Did you understand this, guys? Everyone? Or the anchor actually?
Can you hear me now?
Yes, I can hear you. Yes.
Yeah, can you please explain this part? I think this is important part, what Devendra alluded to, zero constant. Is it like the model will basically find a simplistic, say basically if it model makes everything the same, then the loss becomes zero, and then is it something like that? Then which is not true representation, but from a minimization problem perspective, that is the ideal solution in terms of finding the
Exactly.
loss where the loss is zero. Right, so we want to avoid that part. That means the meaning of the different representations could be retained in somehow. This
Exactly.
that's how this contested learning is coming into play, right? Just trying to build the
Exactly.
understanding. All right.
Absolutely. Exactly. That's the
Hmm.
way. Yes.
Great.
Yeah.
Please carry on.
Yeah. Perfect. Any other questions or comments? Okay. So the contrastive learning came up in this with this motivation that we need to have something like some attractor and some, a reflector. So what they did is, when two images, like if an image is there, everything else is kind of a negative. So they attracted between similar augmentations and ripples between other augmentations. But you may think that this is a basic idea. Okay, so what they did is that they added a term of, so it's just not reduction. So it's not just distance between x1, x2, but also we want to increase the distance between, so minus of the distance between, let's say, xi and yj. So what I'm saying is that x and y are two different images, and let's say, xi and xi dash are two different augmentations of the same image x. We want to reduce the distance, and we want to increase the distance of any two different augmentations of two different images x and y. Yes, absolutely. So coming to this, what Ajay has said, this has been, so one intuition gap here is, what if there are two dog images? Aren't we reducing, like, is it not bad? And that's a later part came up with other ideas of clustering. Okay, the ideas of clustering came up where different clusters of same images are formed, and then the distance between the clusters are created. So many different ideas came up, but the core important idea to note is that this discriminative loss kind of idea came up, where we reduce the distance between two augmentations of the same image or same cluster of images, and increase the distance between two augmentations of two different clusters of images or two different images. Okay, and one issue is that this needs a lot of negatives. And there have been like updates of this by SimClear. So this was by Meta, and this is by SimClear, and this is by Google. And the basic idea, like, it was a similar idea but a different approach. Okay, but they realized that augmentation is very important here. Strong augmentations, different kind of a varied kind of augmentations are important here, which we observe, which we understood in the thought experiment. And the basic formula is clear. Take an image, take two different augmentations, pass through an encoder projection head, get the representations, then there's positive pair and negative pair. Okay, this was the basic structure. But the next question came up is, do we actually need this negatives and positive? Because we need actually a lot of negatives out there. Or, I mean, is there a different approach? The main question came up. And it turns out that yes, there is. And the idea they took was kind of similar to this. So one important thing to note here, understand these two are the same f. Okay, so, and this can lead sometimes, the same function can lead sometimes to model, if one model collapses, the other collapses immediately. So what happens is that when you solve one model collapse, another kind of model collapse comes up. So they build this new structure approach where they have the network, but this is one is a delayed version of the network. Okay. One is a delayed version of the network. So this is called the target network, which we'll see in DINO, it's a teacher network. And one is a student network that it's learning from the target. So how did they do that? So they do it in this, so I will come to that. But one important another idea is that in this target network, the gradients are not updated. It's kind of fixed. It's kind of a delayed version of the student network. Now, why is this important? We will see that this is important because this solves. Yeah, I will explain that, sure. That's what I'm coming to. You see this exponential moving average, I'm coming to that. But what I'm trying to say is that what does this solve? This solves the fact that you have two different encoders, and one encoder is more stable. The teacher encoder is more stable than the student encoder kind of idea. In this case, it's, let's say due to an image update, due to a sudden update, the image encoder collapses. But there's a teacher encoder which is trying to force it not to collapse. So how is this happening? So let's understand what DINO is doing. So in DINO, we have this image. So in DINO, what they're trying to do is that they're trying to understand this global and local views. These are two augmentations that they take. This local and global view. And this is student network and the teacher network. So everything is same, but what is it doing? So this, did I keep that? Okay. So this theta t is nothing but tau of theta s plus 1 minus tau of theta t minus 1. Oh, just give me a minute. Did I write it properly? Yeah. So a delayed version in the sense that it takes a part of the student. Understand, this teacher network is not getting updated. This teacher network is not getting updated like by gradients. It's just a delayed version. Everything is a delayed version. This theta t minus 1 is also dependent on theta s minus 1. So it's a delayed version of the student network. Like you do exponential moving average in financial forecasting, right? It's a delayed version. So it smoothens out. As you know, in moving average, smoothens out, right? Exponential moving average in forecasting. Similarly, the networks are smoothened out. Okay? This is smoothened out by this moving average. And it is not updated. Now, you can mathematically prove, just like the EMA, it's smoothened out version of the stock market. Similarly, you can mathematically prove out here that this has lower bias plus variance square. Actually, variance, bias square plus variance. And empirically, it has been shown that this has higher accuracy and lower loss. Let me try to show you the DINO paper. So you can see here. Why? Because this is generalizing really well. Since the variance square is low, sorry, the variance is low, so bias square plus variance is actually lower. So understand this. Understand this, that if you average it out, both as time progresses, both will have the same parameter with time. But if you calculate the variance of it, you will see that since both tau is less than 1, the variance will be smaller, because an average variance is smaller than the individual variance. That 1 by n term is there, right? Variance of 1 by n summation xi is variance of each of them by n. So it's less. So this smoothing property helps in reducing the variance, increasing generalizability, because the generalizability is this is captured by this variance variant trade-off. So the bias anyway in the long term goes to 0, but this variance is reducing. So this increases the generalizability power of the teacher network. And that's why you can see that in the teacher network, it's becoming better. It's guiding the student in a much better way. Okay. So what I will do is that since there is not much time left, actually we have passed the time. Okay. Let me discuss a few things, and if needed, we will do another session on this. One important thing is that there's a centering that happens. By centering on the teacher's framework, the centering happens. So what centering does is centering makes the teacher's network the value 0 on average. Okay. So let's not rush through it. So I will discuss this center collapse later on if we have another session again. But another important thing, and let me tell you the progress of how the entire thing happened, how this progressed. So there are a few measures like sharpening of the temperature or the distance, which also helps us in reducing the collapse. So there's a few simple mathematics that needs to be discussed. But let's move on to the idea of what happened in the future aspects of DINO. So after this DINO was in 2021. Okay, in 2020, in the next year probably or 2023, the mask autoencoder came. Remember that the autoencoder we discussed initially, the image, and we reconstruct the image. But what they discovered is that they took the idea of this masking from BERT, the language model, and they masked the image at certain places. And they tried to reconstruct it. And it worked really beautifully. In fact, when they have a high masking around 75%, it really gave well. Because understand, in image, there's a lot of correlation out there of one patch to another. There's a vision. So this led to the idea that masking actually can give. So there's no contrastive loss, just masking, just reconstruction with masking. The same idea from 2006, just with masking with large amount of data worked really well. Okay. So what DINO 2 did was DINO 2. So just this is the last discussion slide. DINO 2, there's also in DINO 2, DINO version 2, there is also another data preprocessing, okay, which help them understand and collect good amount of data. So DINO V2 is mostly about scaling DINO to large amount of uncurated data, just like the LLMs are trained on uncurated like web text. I mean, there's some curation out there, but yeah. So they did an important data preprocessing pipeline for the scaling up. But in DINO V2, they added this extra patching thing, this masking thing. So there is one encoder which looked at just the previous aspect of the similarity of the two augmentations, and there's another encoder where the patches were removed and the patches were reconstructed. So the student patches were removed, the teacher patches were kept, and they tried to reconstruct the teacher's patch from the student's patch. So this was motivated. This is called an IBOT loss. This was motivated from the mask autoencoder decoder. And yeah, so there are other few things. I think if I have another session, that will be better, I believe, for the discussion, because yeah. So in our next session, probably we will discuss about why this centering, why this sharpening actually helps also in more like prevents model collapse. And we also discuss this DINO V2 data preprocessing pipeline. We'll also discuss the Collier regularizer, which enhances the entropy of the features. Okay. And then DINO V3, where the gram matrix is also used. Someone mentioned gram matrix in the beginning. It's actually, DINO V3 is really beautiful, actually. So I will discuss that in the next session. Yeah, any questions, guys?
Excellent session, Srijit.
Thank you.
One question, a question I wanted to check, or basically not a question, but I wanted to understand if I am getting it right or not. I see that, CNNs are something like, say, for example, if I want to picture an scenery or image, CNNs are in the first or second layer itself, you will convert into the non-spatial or non-image type. Say, for example, I will convert it to words saying that there is a river, there is a mountain, there is a sky, sun. Like it's a different representation and different layers. And we don't have a residual connectivity there. So that means I will create one picture in terms of from picture to words, and in the next layer, I could basically create some more classification from those words to whether it's a beautiful or not so beautiful or average, that kind of a, classification and restructuring. So the meaning is getting changed and not preserved. Whereas if you look build a skip connection, that could be treated as you're pretty much trying to build in the similar fashion. S- At the lower level of understanding or learning, it could be like a child trying to draw that scenery in a paper with a rough sketches. The better learning could be, a better painter, and a higher learning could be somebody with the 4K camera taking that snapshot of that scenery, because we are trying to improvise on that residual connectivity by adding up more variations or information on that. Means, of course, not from a working perspective in transformer, but from a concept perspective. Because working, of course, we know that the layer task is quite different. It's just to predict the next token, and it is not a similar kind of analogy. But question here is this right way to try to understand the convolution part?
Yes, so I this is how I think of convolution. I think of it as feature extractors, okay?
Mhm.
And the reason is the skip connection is not also reminding the net, because as it goes deeper and deeper, as we have discussed, the previous information gets lost, because there are a lot of compositions out there. It wants to remind that. And how do you know that? The reason is that the gradient doesn't flow. So there's something called vanishing gradient on exploding gradient problem, where the gradient, when you multiply, it becomes really large or really low, because the gradient contains the information. So you can read this residual network and the skip connection paper, and they will say, so essentially what happens is that in the gradient, so let's this x, and you get f of x, and here you get f of x plus x. So if the gradient of del f, or yeah, so del L del f. So essentially what we are doing here is that we have df, we have to write the entire math out there, but when you do the derivative with respect to x and this one gets added, that reduces the vanishing gradient problem.
Totally,
So
because if you have the residual, that will keep it more stable, because whenever you are doing the back propagation from learning, right?
yes, yes, yes,
Okay.
yes. So Devendra has some comments, you should check it in the comment box.
Yes. Thank you.
Yeah. So yes, the weights are of course not dynamic, because yeah, different. Yeah. Yes. So any more questions? So I would like to discuss with Devendra and get his insights on why he like understand his insights and why he thinks about the hierarchical thing. If anyone wants to have some questions, feel free to ask. So Devendra, can you unmute yourself and discuss with me? I would love to understand your perspective.
I mean, in CNN, basically, we trained with fully connected network before and it didn't work, right?
Yes. Sorry,
Early in
CNN.
the
Can you
so
repeat once
let's
again?
say
Sorry.
if I was working with images,
Mm-hmm.
long back, fully connected networks were not working.
Right.
Then we kind of used the structure of the inputs and we thought, okay, convolution will work.
Mm-hmm.
And we kind of combined this local information and because of that, if I go up in the hierarchy, local
Mm-hmm.
information can be combined to a more global structure. You can justify in various ways, including receptive fields or whatever, right?
Mm-hmm.
And after, like, let's say after 10 layers or something, you would assume that it would be fine, but then we continue to go to 100 layers.
Okay.
But here in transformers, in the first layer itself, we have kind of like a global context,
Yes.
and I don't have any deeper insights to why I need 50 layers, right?
Mm-hmm.
And plus, we also have multiple heads in layer one also.
Right.
So it's already like it's already like a manifold in layer one itself, because there are so many
Mm-hmm.
heads
Yeah.
learning different perspectives. So I'm not able to understand like why I need 50 layers. The only thing I can say is that empirically it worked. But yeah, I mean, I would love to know your comments, but I don't understand why
Okay.
it
So I
should
may be
work.
wrong, Devendra. I may be wrong. Thanks for insight. I may be wrong, but this is my hunch. And if I will do more research into it. But this is what I've learned. If you know something different, I would love to learn from you. So feel free to ping me on LinkedIn or email, whatever you want. But this is my understanding that I believe, first of all, as you said, that each attention, that entire attention is equivalent. I am thinking like this, okay? Each attention key query value and the update key query value, this I am thinking as equivalent as the channel output, okay? The stack of attention, the multi attention, I am kind of, but you're right, there is a sequential aspect to it. But I used to think of as a channel of attention. So each attention is one filter. A channel I was thinking as a multi attention, okay? And so that becomes one layer. So I was thinking in this way. So from this diagram, so this is one layer for the convolution, and this is one layer for, I was thinking the not into L. This is not there. Just into one. I'm thinking of this as one layer. The attention is equivalent to convolution in my thought process, and the number of channels is equivalent to the number of number of heads. So in that process, I thought, okay, if this is the analogy, then the layers of convolution will be similar to the layers of VITs,
Okay.
because the hierarchical process is the same.
Srijit,
But
Yeah, even
yes,
if you look at
that's
the
my
heat maps, as you go into depth of the layers, as you go
yeah.
higher up in the layer, the attention maps get more